Hey guys, and continuing straight on from the previous video. So we're now up to finding the compression in the steel. So what we're going to have to do is come to our strain diagram and draw in the steel strain. Okay, so those lines correspond to where the steel is in strain, or the steel straining. So I'm going to call that strain 1, strain 2, and strain 3. So that's for layer 1, layer 2, and layer 3. Now the first thing we need to do is actually find the strain in the steel. Now the way we're going to do that is just by similar triangles. Okay, you can see we have a triangle here, 0.003, and we're going to find E1. So when we do this, we always need to check it against our yield strain. So you'll see what happens in a sec. So let's go find. So strain 1 on. So I'm doing this big triangle. So this triangle, so the E1 all the way there to 0.003 all the way there. So this triangle and that triangle. So the small e on 0.003, so that side on that side on 0.003 is going to equal, now we're going to look at distances. So the distance from there to there would be 200 minus 185. So this distance from there to there is 200 minus 15. So that would be 185. So this is equal to 185 on top of the 0.003 has a distance, the full depth, so 200 on 200. If you were to solve this for little e1, so you would find you would have a strain of 0.0028. Now what you always have to do is check it against the yield strain. So we found the yield strain in the previous video. In the squash load, we saw that the yield strain was 0.003. So we need to check 0.0028 against 0.003. So 0.0028 is less than 0.003, and therefore it hasn't yielded. So there's no yield, which is good. Now, if there was yield, I'm going to talk about a little bit later in this video what you would do. But just assume that it's all not yielding. So this is definitely is not yielding because it's less than the yield strain. Now we need to do this same process for the other two. So let's just find the compression in this first. So the compression in the steel one is going to equal the strain times by the elastic modulus times by the area of the steel. So this is the same as the stress times the area. So solving this, the strain we found is 0.0028 by 200,000 by the stress, sorry, by the area. So the area of steel corresponding to 1, that layer there is 2 bars. So it's 2 by pi, and the radius of the bar is 6, so 2 by pi by 6 squared. If you were to work this out, you would find you'd get a value of 125.5 kilonewtons. Now, let me tell you what's going to happen if this did yield. So let's say, for example, that this is not happening. This does not happen in our example, but let's just say something like this were to happen. So we have the same yield stress, 600, the same yield strain, 0.003, so 0.003. Let's say we found that E1 was 0.004. So in our case, E1 was 0.0028. Let's say it was 0.004. Now, because E1 is now greater than the yield strain, so 0.004 is greater than 0.003, it's actually yielded. And then to find the compression, it's just going to be the yield stress times the area. So it would just be 600 times the area. So you can see the difference. In this one, we worked out the strain, and we had to times the strain by the elastic modulus times by the area of steel. That gave us the force, the compression. If it wasn't the case, if it was that it actually yielded, you would just go straight to the yield stress. Because it's yielded, the maximum it can take is the yield stress. So it would just be the yield stress, 600 by the area. In this case, it hasn't yielded yet. It's at a strain which is less than the yield strain. So you have to go find its corresponding stress by multiplying by the elastic modulus times by the area, you get the force. So that's the difference between the two. This like type of problem here where it's yielded, we're going to see that's going to happen later on when we come and find the pure bending, which is a video later on. You'll see we're actually going to have to apply this process. But I just wanted to show you at this stage that it could happen that your steel actually has yielded. So that's what you would do. Once again, we're going to be seeing that later on when we find pure bending, because we're going to see that our steel actually does yield. So we're going to do the same process now for the other two layers. So for E2, so E2 on, so we're doing this triangle now, and the big triangle again. So it's E2 on 0.003, so just by similar triangles, equals this length from there to there would be, so it's 100 and 100, it's in the middle, so it's just going to be 100 would be that length there. So 100 on, and 0.003 acts on the full length there, that triangle there, which is a depth of 200. If you were to solve this, you would get E2 equals 0.00015, which is also less than 0.003. So it's less than your yield strain. So this also has no yield, it's not yielded. And therefore we can find the compression in our steel 2 would equal E times AS, so the strain times the elastic modulus times the area, which is the same as the stress times the area, which is, the strain is 0.0015 times by the elastic modulus, which is 200,000, times by the area of the steel. So once again, we're at layer 2 here, and we have 2 bars, so it's going to be 2 by pi by 6 squared. You would find that you would get an answer of 67.9 kilonewtons. Okay, the last one we need to do is the third layer, this strain 3. So E3, so we're taking this tiny triangle here and this bigger triangle here, bound by 0.003. So it's E3 on 0.003 equals, so this tiny little height there would be 200 minus 185, so that height there is just 15 mils. So it's on 15 on top of, once again, the big triangle is 200, so 15 on 200. If you were to work out this strain, so the strain in 3, you would get 0.000225. So let me just double check that. So we're going to have 15 divide 200 times by 0.003, sorry, 15 divide 200 times 0.003, we get you so 0.000225, so that would be the strain. Once again, this is less than 0.003, so therefore it has not yielded. We're going to find the compression in steel 3, which again is the elastic modulus times the strain times the area of steel. So this would equal the strain, which is 0.000225, times by the elastic modulus, which is 200,000, times by the area of the steel. So this time we're at layer 3. We have 3 bars, so it's going to be 3 by pi by 6 squared. And if you were to work this out, you would get 15.3 kilonewtons. Okay guys, I'm going to continue in the next video where we just go and find the axial force and the moment for the decompression point. Hope that helps guys, we'll see you in the next video.